Hi, I'm Hila from the Tangible Media Group in MIT Media Lab, and today I will be presenting Venous Materials towards interactive fluidic mechanisms. So what is Venous Materials? It is a novel approach of programmable material using interactive fluidic mechanisms. And we define these fluidic mechanisms as embedded analog sensors and displays that respond to physical deformation input. This project is inspired by vein systems that are ubiquitous throughout nature and in the human body. And beyond the functionality of the transmitted fluids that flow through the veins, these structures can use as analog indicators and sensors. And for example, veins in leaves transmit pigments that drive color change, which then inform us of the leaf's internal condition and also on which season it is. Embedding the interactivity in the material itself has been explored in programmable materials in HCI. And the main idea of this research is that the researchers pre-program the properties of the material to respond to specific external input, such as mechanical force, heat and humidity, pneumatic and fluidics. And in pneumatic and fluidics, most of the research is using external pump to actuate the inflation or the flow, and we take a different approach in this paper. Researchers in the field of microfluidics expertise the manipulation of fluids at the microscale. They created lab-on-a-chip applications, on-skin devices, soft robotics, sensors, and integrated biological systems. And all this research is really interesting to us, and here in this project we utilize the microfluidics technology to create a new category of interactive programmable fluidic mechanisms. So our approach in this paper is that we consider the fluid as a medium to drive the tangible information and at the same time to function as a responsive display of this information. The characteristic of our material is that first it's deformable, so the deformation is what driving the flow through the material. And this also makes it self-contained, so there is no need of battery or any external pump. It's also transparent, so the user can see through the logic and the structure of the flow. And we use minimal amount of components, so it's easy to manufacture and recycle. So today we're going to speak about this very basic mechanism and architecture that we studied and developed. And from this basic mechanism, we created different configurations. So as you can see in the back of this slide. And so to do that, we will go through the mechanism, the design space, the design and simulation tool, the fabrication process, and the applications. So let's start from the basic architecture of the mechanism. So we have the silicon substrate material, and within this material we have a fluidic channel that is connected to a fluid repository, which contains the fluid material, and also connected to an air repository. So the way the system works is that when we apply pressure on the fluid repository, the air in the air repository compresses and the fluid flows through the channel. So that's the basic architecture. But by changing each parameter in this architecture, we can really program and control the interactivity of the material. So now we see how we do it in the design space. And we will go through each part: flow and display, compositions, deformation inputs, and utilities. So let's start from flow and display. In the flow primitives, we start from the very basic flow behavior, which is continuous, split, merge, intersect, or irreversible. And we combine these flow primitives to create more complex geometry patterns, as you see on the right. We also created multicolor primitives, which is mixing, gradient, overlay, and interweave. And deformation inputs is what is driving the flow through the material. Venous materials can respond to various deformation inputs such as a pressure, which contains pressure point, area, and a slider, and more complex deformations such as bending, stretching, and twisting. We have two types of compositions. We have layer compositions with single layer, multi-layer, isolated, and connected multi-layer, which is 2.5D. And we also have iospatial compositions, where the display and basically the input and the output are either transmitted over distance or collocated on the same location. So with all the primitives that I just showed, we created utilities, which is the basic functionalities that we use to design the interaction with Venous materials. And we have two types of utilities. We have pressure visualization and dynamic motion display. And today I want to highlight one of the most interesting utilities that we achieved, which is that beyond the real-time response, we can capture the pressure as a memory in the material. And here we capture the droplets in the mesh geometry to represent the increasing applied pressure. And in this second example of memory utility, we use both mixing and branching to capture the pressure memory in the central repository. So here you can see the pressure reaches the first branching point and the pressure level, and mixes with the pink. And here you can see the fluid reaches the second pressure level, which is blue, and mixing to create purple and indicate this is a higher amount of pressure. So now that we went through the design space, we can see that Venous Materials has more complex flow behavior and design geometries. And this might not be easy to understand and design. So one of the questions that really motivated us was, how can we allow designers and researchers to plan and simulate Venous Materials? So we created the design and simulation tool, which is the first step of our fabrication pipeline. In the design and simulation tool, we developed both the tool itself and the UI to plan and simulate the flow according to specific deformation input. And here you can see the user first generate the geometry, and then he can modify different parameters and then simulate the flow according to either pressure actuation or bending, which are the two actuation we implemented, and then finally simulate and see the visual result. Our simulation method aims to calculate the dynamic flow map, and we do that by first dividing the channels into cells and then iteratively comparing between the resistant pressure map and the actuated pressure map. And the technical evaluation included mechanical testing of pressing and bending and the correspondence flow to these actuations. And we use this data to evaluate and optimize the simulation method. And this evaluation showed correlation between the simulation result and the actual fluid flow. So now that we went through the design tool, we can go to the fabrication pipeline. And after we prepare the PDMS, we laser engrave the material, and then we manually layer by plasma bonding or self-adhesion. And finally, we inject the fluid and seal the material. So how can we embed Venous Materials in everyday life to create new experiences? As Venous Materials are deformable, they can be embedded in wearables to visualize on-body motion, pressure, and body balance. They can also be attached to objects for learning activities. And in the shoe example, the shoe prototype is designed to visualize the pressure that's applied on the shoe sole, while the display itself is located on top of the shoe. And this can be used to raise the awareness of the user to their body balance for rehabilitation and dance lessons. And our other examples include learning activities, where in learning it's often required to have granular understanding of the motion or pressure that one should apply on a piano key or a paintbrush. And this way, this can be visualized during the learning process using Venous Materials. In everyday life and everywhere around us, we use graphics. We use signs and lines and text and graphs. Yet all these are static. What if we could use Venous Materials to make this graphic dance? So in these applications, we engage the user by tangibly giving him the experience of tangibly manipulating the graphics and the information. For example, in the Chinese letter application, we utilize the sequential nature of the flow to visualize the order of writing the Chinese letter, which is very important when learning Chinese. And in the graph application, we allow the user to dynamically manipulate and tangibly manipulate the flow and the data. In packaging, it often requires cheap and simple analog indicators. And we think Venous Materials has a great potential in this field to both transmit the information from inside the package to outside, and also to capture the external pressure as an indicator for the delivery process. To summarize, Venous Materials is a novel approach of programmable materials using interactive fluidic mechanisms. To show that, we designed and studied a basic architecture of the mechanism. Then we expanded this to a wide design space as a design tool and a toolkit to designers and researchers. We implemented the design tool in simulation, and we developed a fabrication process. Finally, we demonstrated a variety of applications. So what is the next step? As the title of our paper implies, Venous Materials and the work in this paper is a very first step towards a broader research idea and a vision of interactive fluidic mechanisms. And beyond the current limitations, there are very exciting future work that we can do. So for example, how can we go beyond 2.5D? So we think 3D printing is really a great opportunity to create more robust and automated fabrication system. And how can we embed the more complex logic in the material to create user interfaces and embed computational logic as part of that? And the most interesting thing for us is how can we create more advanced interaction modalities? And the idea that we can introduce to the system any fluidic material with different properties, this can help us to go beyond visualization to shape changing or stiffness changing or other properties that are dynamically controlled and programmable flowing through the material. This is a really interesting opportunity for us. So the main message of Venous Materials is that this new perspective of the fluid as a medium to drive tangible information, and at the same time function as a responsive display of this information. And we think this is a really important paradigm in HCI. And with this new paradigm, it's really exciting to think about how to imagine the world with this new type of interactive fluidic mechanisms. And it's a great opportunity to design these mechanisms to be embedded in objects across scale and across different functionalities, from books and packaging to instruments and wearables and interior design objects and more. With that, I would like to thank all of my co-authors on this paper, and thank you for watching this talk, and please feel free to reach out with any questions. Thank you.